The reaction in which water molecules produce ions is called the self-ionization of water. So we can see that water can break up into a proton, H+, and a hydroxide ion, OH-. So here's how that happens. If we have two water molecules, one hydrogen can be donated to a water. And what you get is hydronium and hydroxide, or what you can think of as an H+ and an OH-. Self-ionization of water occurs to a very small extent. Only some of the molecules are actually becoming hydroxide and hydronium. The majority of them stay as water. And water is considered a neutral substance because the amount of the proton and the hydroxide are equal, or the hydronium and hydroxide, they're going to be equal. In an aqueous solution, when hydrogen ion concentration increases, the hydroxide concentration decreases, and when the hydrogen ion concentration decreases, the hydroxide ion concentration increases. Acidic solutions have a hydrogen concentration greater than 1 × 10 to the -7 molar solutions. Basic solutions are less than 1 × 10 to the -7 molar solutions. So basic solutions are known as alkaline. Other than just saying basic, you'll hear people say that it's more alkaline, meaning more basic. The pH of a solution is the negative logarithm of the hydrogen ion concentration. So we write it out like this: pH equals negative log times the hydrogen ion concentration. And here's what that does for us. When we look at the pH and the concentration, you'll see what the correlation is. From 0 to a number slightly less than 7, we will call those acids on the pH scale, and the concentration will be 1 × 10 to the 0 power, all the way up to just before 1 × 10 to the -7, which would be neutral. So 1 × 10 to the -6, -5, -4, and so on. All those concentrations have a pH between 0 and 7, and those are acids. If it's more than 7, all the way up to 14, those are bases. So that'll be up to 1 × 10 to the -14. Notice the pattern in the exponent. And then 7 is neutral. The pOH of a solution equals the negative logarithm of the hydroxide ion concentration. The basic rule is that the pH plus the pOH will always equal 14. So if the pH is 6, the pOH is 8, because they have to equal 14. Now another way that we can look at this is that pOH is equal to the negative log of the concentration of OH, or hydroxide ion. And visually we can see the relationship that we have. As we have a higher concentration of hydronium or hydrogen ion, we have a lower concentration of hydroxide, and vice versa. And when they're neutral, they're both at 1 × 10 to the -7. Hydrogen ion concentration should be written in scientific notation to denote significant figures. The pH scale has typically one significant figure if we're looking at just whole numbers, like a pH of 1. There's also one sig fig. So let's try a problem here. What is the hydrogen ion concentration of a solution with a pH of 8? Well, we know our equation is that negative log times the concentration of hydrogen ions is equal to the pH. So first we'll just rearrange some things. We'll move the negative sign, and we'll plug in our number for pH. And in order to get rid of the log, we have to do the anti-log, which on your calculator is 10 to the x of the -8. And what we get is 1 × 10 to the -8 for the concentration. What is the pH of a solution with a hydroxide concentration of 2.0 × 10 to the -10th? So we've got to remember a couple of things. First, we know that the concentration of hydrogen ions times the concentration of hydroxide ions is equal to 1 × 10 to the -14. If we rearrange this equation to solve for the concentration of hydrogen ions, what we get is 1 × 10 to the -14 divided by the concentration of hydroxide ions. And we have the concentration of hydroxide ions in our problem, but we're trying to get to pH. So the other equation we know is that the pH is equal to the negative log times the concentration in hydroxide ions. So what we're going to have to do is solve for concentration of hydroxide and then plug that into our pH equation to get pH. So what we'll start with is to find the concentration of hydroxide or hydrogen ions. We do 1 × 10 to the -14th divided by 2.0 × 10 to the -10th, and we get the concentration to be 5.0 × 10 to the -5th for H+. Now we can plug that into our pH equation. So we plug the number in for concentration of hydrogen. pH equals negative log times 5 times 10 to the negative fifth, and we solve that our pH is 4.3. An indicator is a valuable tool for measuring pH because its acid form and base form have different colors in solution. Temperature can affect the indicator's usefulness, or it can be distorted if the solution being tested is not colorless, so there are problems with indicators, and it can be better to use pH meters instead of indicators. But what you get with indicators are the little different color ranges, and these are some types of indicators that we have used in the lab and that scientists use as well.